Welcome to this video on copper versus aluminum bus bars for electrical panels. This is a classic debate in electrical engineering. We will give you a comprehensive breakdown of the core comparison. At a glance, copper offers 100% IACS conductivity, high density, and excellent corrosion resistance. Aluminum is about 61% conductive, significantly lighter, and costs 3 to 4 times less than copper. Copper's advantages include the highest conductivity, allowing for compact panels. It also has excellent mechanical strength, superior creep resistance, and is easy to weld. A key benefit is that copper oxide is conductive, unlike aluminum oxide. The main disadvantages of copper are its high cost, which can be 3 to 4 times more than alternatives, and its heavy weight. This added weight necessitates stronger structural supports and makes installation more difficult. Copper is the superior choice for compact panels, high short-circuit levels, and mission-critical installations like hospitals. It's also preferred for marine and offshore and high-temperature environments due to its stable performance. Aluminum bus bars offer significantly lower material cost, leading to major savings, especially for large panels. They are about 50% lighter than copper for the same current rating, reducing support structure cost. Aluminum also has good availability. Aluminum's disadvantages include the need for a 60% larger cross-section, increasing panel size. Its oxide layer is non-conductive, requiring special surface preparation. Aluminum also suffers from creep and thermal expansion and bimetallic corrosion when directly connected to copper. Aluminum is best for large distribution panels, where space is not a constraint, and for cost-sensitive projects. It is also ideal for applications where weight matters, such as transportation and marine, and for fixed installations with minimal temperature cycling. For the same current capacity, aluminum requires a 60% larger cross-section, but it is less than half the weight per meter of copper. Aluminum's material cost is 40% to 50% lower, though it requires a larger panel space. Critical design considerations for aluminum bus bars include using stainless steel or zinc-plated hardware, never dissimilar metals directly. Bevel washers and proper torque are necessary to maintain pressure. Always apply an antioxidant compound after wire brushing contact surfaces. Thermal expansion is a key concern, as aluminum expands about 35% more than copper. For long bus bar runs, implement expansion joints like flexible braids or sliding connections to prevent mechanical stress on the joints. Regarding the skin effect in AC systems, for typical industrial bus bar sizes, the difference between copper and aluminum is negligible. However, for very high currents above 3000 amps, consider using hollow or channel sections to mitigate the effect. In terms of short-circuit withstand, copper's higher yield strength allows it to handle higher fault currents without permanent deformation. Aluminum bus bars may require closer support spacing to handle the same fault level. The decision matrix recommends copper for compact panels and high reliability needs like data centers. Aluminum is recommended for large switchgear, cost-driven projects, and utility substations due to significant cost savings and proven track record. To maintain credibility, reference standards like IS 8623 and IEC 61439 for switchgear assemblies. IS 61347 and IEC 60947 cover requirements for bus bar joints, and IEEE STD 605 provides guidance for bus design in substations. Thank you for watching this video. If you found this information useful, please like and subscribe for more content.